So these are the code we can use. Since the analytical solution is given, we can use this kind of code to find the numerical solution in impulse responses. So this is the numerical solution of the system for impulse responses. And also for this code for step responses. So we can solve the problem in this way. But actually, I'm not quite happy with this method since there are too many limitations, restrictions. One of the limitations is that if you want to solve this problem, the system must be a commercially ordered system. But and also the terms must not be too much. Otherwise, you may find problems in finding the partial fraction extensions or something like that. So this is one limitation. The other limitation is that this method can only be used for examining the impulse responses and step responses. If you have a signal like this, if you use this signal to drive the system, you will not get anything. So there are too much limitations. So now let's consider an alternative way for solving the problem. Let's go back to grammar-analytical definition of fractional order differentiation. This is a standard definition. I think Professor Leo presented this part to you. And by the use of this definition, where the binomial terms can be expressed in the iterative way, like this. And by the use of this definition, I think we can easily write a method function to calculate the fractional order differentiation to a given signal. And I think Professor Lee also said that this definition is equivalent to the Riemann-Royal definition, but it is slightly different from the Capaldo definition. I think the definition, the difference is something like this. If the original signal is defined like this, this is the t equals to 0. Then if we take the grammar-analytical definition to the signal, it will regard that the function when t is smaller than 0 is 0. The function value is 0. So there might be a gap here. However, I think if you are using the Capaldo definition, what you have to assume that for t is smaller than 0, the function should be extended like this. So this might be the difference. I'm not sure whether this one is strict or not, but that's my impression. And for control systems, normally the system to be controlled is at rest in the initial time. So the initial values should be 0. I'm not quite sure whether this is strict in mathematical terms. So in this case, I think we might be using the grammar-analytical definition. And also this definition is quite easy to use. So I write a function myself to calculate the fractional order differentiation to a sequence y, a signal y. We have some simple point in y, and we can call the function glf, diff, and we have y vector, t vector, and we can specify the order. Then we can find the derivative of it. And this is the function itself. By the use of this function, you can easily observe the fractional order derivative of a certain function. and you can draw three-dimensional paths. One axis is the order of differentiation, the other one is t, and the other one is the fractional order differentiation of the signal. However, in control, this kind of definition or this kind of code has limitations. The most important one is that y must be known before you calculate the differentiation. Y must be a given vector. However, in control, y might be a signal generated by a certain block. So we cannot use this kind of definition. This kind of definition can only be used for offline computation. So there are limitations there. And so it cannot be used within the system. And also, we can think about ways to validate the result if y is given before computation. If y vector is given, then we can consider which result the result we obtain, we can check whether it is correct or not by changing the calculation step. If we change the calculation step and find that the two results are exactly the same, we will say that the result is accurate. Otherwise, you have to reduce the size of the step. So we can, after computation, we must validate the result to see whether the value of h is given as a correct value. Based on the GL definition of fractional order differentiation, I think we can easily find the closed form solution of the differential equation like this, where the right-hand side is given by a signal. It is not necessary to be a stack signal. It can be any sequence of signals. So how can we find the result like this? If we let's recall the GL definition. Well, in the definition we have a sum of terms to represent this kind of fractional order derivative. So in the term, we may have a y term, there is a weighting, and also there are y terms in previous times. I cannot remember how to write it in a strict form. So in each of the derivative terms, we may have a y term. Current time, the output signal at current time, we will have a y term, and we will have a sequence in the past times, the y values in the past times. So for each terms, we have a similar thing. So now we have to add these terms up. If we add these terms up, these are the sequence with different weightings for the current value of y, and these terms are for the past values of y, and we can move this part to the right-hand side of the equation, and finally we should get the closed form solution of the system like this. It could be rather complicated to derive it, but I think it should be correct. So this is the closed form solution where we can solve the problem in numerical ways. And there are limitations that the right-hand side of the equation must be a U signal. It cannot have differentiations of any order. So there are limitations in this computation.